Welcome to Minukuu tutorials. Today we're going to see how we can perform McNemar's Chi-square test of independence in R or RStudio. So basically, McNemar's Chi-square test of independence is usually carried out to assess the relationship between two paired nominal variables, and these two paired nominal variables must be dichotomous each. That is to say, each must have two responses or modalities, yes or no response, basically. So at the end of the day, we will have a 2 by 2 contingent table, and the two groups of data must be paired, or in other words, the two groups of qualitative data must be paired. So here, what I mean by k is equal to 2, I'm referring to the number of paired groups. So we have two paired groups. Okay, I have these contingency tables right here that's the actual examples. For the first one, we've already carried out the McNemar's Chi-square test, and that's what we repeat for you and see whether we can obtain these answers as I explained on R or RStudio. So looking at the first example, what can we say? We have two test kits, kit A and then kit B. Now, these two test kits were used to, for instance, carried out diabetes test in, what should I say, a sample of, let's say, 20 patients. So what happens is that the response variable here is the same, is what? The status of the health status of the patient. Either the patient is diabetes positive or diabetes negative. So using these two kits on the same patient makes the two groups paired. That is, we have what group of test results for kit A and then the group of test results for what kit B, but both results were obtained from the same patient, the same 20 patients. So for that matter, that's to say, when we talk of paired data, we could either, they are usually longitudinal or repeated data, and then this repeated data is either the measurement has been done, let's say, at different time intervals. For instance, we can take the temperature of patients in the morning and the temperature in the afternoon. The measurements taken for all the patients in the morning and the measurements taken in the afternoon, these two groups of data constitute what? A paired group, or let's say paired groups of data, or a paired group of data, let's put it that way. Another example is when the procedure can be repeated but with what? Different instruments. So here we are not really interested in the time factor, but with different instruments. For instance, in our case, test kit A and test kit B, measuring the temperature with thermometer A and then thermometer B, but both groups of qualitative data will be obtained from the same patient, so we term that as paired data. Remember that the variables must be qualitative, in other words, nominal or categorical, and they must be paired, and they must be what? Dichotomous, for us to have the 2 by 2 table and for us to be able to perform the McNemar's test. If the variables are not paired, then we have to conduct the Pearson's chi-square test of independence with or without Yates correction, but not McNemar's test. Before we can perform McNemar's test, it must be what? 2 by 2 contingent table. That's two dichotomous qualitative, in other words, nominal variables, and these two variables or the groups of data that we are going to collect must be paired. So it's either repeated data, let's say it's either repeated measurement for the same group of patients using the same instrument, that's so at different time intervals, or using different instruments to measure the same thing in the same patients. That's why we simply term as paired data. So you can, as you can see in the second example, we have what the patient status before and after treatment. So before treatment is dichotomous, sick or not sick. Here the response variable is what? The disease, sick or not sick. And then the independent variable will be the time. In the first example, the response variable is what? If you want the, what do you call it? The test results, or in other words, the diagnostic. Positive or negative, that's the response variable. And then the independent variable will be what? Test kit A or test kit B. In the third example, we are treating the patients with different drugs, for example, treatment A and treatment B, but on the same patient. So the response variable here is what? Whether the patient has recovered or not. So it's recovery. And then the independent variable will be what? What treatment was used? Treatment, so treatment A or treatment B. I hope this is clear. And we can now go ahead and perform our McNemar's Chi-square test of independence. I have the data right here, and then I've already saved it on the desktop in the form of a CSV file for the importation. So this is just the first example that we saw, test kit A and then test kit B. So at the end of the day, the aim of McNemar's Chi-square test of independence is to test whether these two groups are independent. Let's look at it here. Is to test, like for the first example, it's not like, unlike in chi-square test, in McNemar's test, because the data is usually what should I say, the groups, it's just more or less like we are crossing the same thing. For instance, kit what should I say, kit A and then kit B, you realize that the modalities, in other words, is the same thing, negative, positive, but with different instruments. So we are crossing them. And then what will you be interested in? B and C. That's to say, if the two test kits are independent, then the null hypothesis must be true. In other words, the proportion of patients that were tested negative by kit A but tested positive by kit B must be equal to the proportion of patients that were tested positive by what? Kit A but tested negative by kit B. Alright, so let's go ahead and perform our McNemar's Chi-square test of independence. To import the data, I prefer using the command read.csv2. You could use read.table, whichever that you like. I like this one because it's much more simpler. And then you get onto your desktop or wherever that you have saved your data set in the form of a CSV file. I saved it on the desktop. Let me show you. Right here, this is the data set. So you right click on it. For those who might not know how to import a data set, you right click on it, then you click on properties, you click on security, and then you copy the file extension. Control C. Then after copying the file extension, you simply get onto your R Studio or R. Then you read I'll call the data set base. So the command read.csv2 into brackets, you paste this in quotation marks, and after which you change this. So backslash, you put normal slash or /. Then you execute to import your data set. And as you can see, the importation is done. To print, you can print our data set to see. Here it is. It's well imported. Okay, kit A, kit B. And now if we want to see the first 6 rows, then we use the command head into bracket the name of the data set, and it has given us first 6 rows. If you would like to know how many patients, to know the number of patients, we use the dimension command. So dimensions, you put the name of the base, the data set. I call it database, so base, and it's telling us that we have 20 patients, and then we have 2 variables, kit A and then kit B. It's important to know the form of your variables, in other words, the structure of your variables, because as I said, in performing McNemar's Chi-square test of independence, the 2 variables must be dichotomous, they must be nominal, and they must be paired. So more importantly, they must be what? Qualitative. In other words, they must be categorical. They should be in the form of factors or characters. And as you can see, they are in the form of factors with 2 levels, negative, positive, negative, positive. So that's okay. If, on the contrary, if let's say R had recognized them after you've executed str, in the bracket the name of the base, if R has recognized them as numeric variables, you would have had to use the as.factor command to convert each of them into what? A factor. And after which we now have to attach our data set, so that each time we want to write kit, for instance, variable kit A, we simply write its name instead of saying base $kit A. So we have to attach our data set, and that is done. Now let's go ahead and construct our contingency table. There are different ways of doing it. You could use the simple table commands. For instance, you say table, and then use the table command, table into brackets, kit A, comma, kit B. You have the choice. You could use this, or you use the xtabs command. Then you write the xtabs. This is the formula, the command, xtabs, and then you write the formula, tilt, and then you write kit A plus kit B. The name of the data set, we called it base. So you write base. It's the same thing. So if I should execute this, it will construct our contingency table. And let's print the table. As you can see, here it is. Kit A, kit B. It's telling us that there were actually no patient that was detected by kit A to be positive, and at the same and negative by kit B or test kit B. And as you can see, I've already have my results here. So positive, what should I say, positive for kit A and negative for kit B is 0. Then we have 785. So it's the same results that we've obtained here. Okay, now we have our contingency table, but these are actually the counts. If we want the percentages, in other words, the column percentages or the column proportions, we will have to install a package known as desc-r, and then desc-r contains a command called cross table, and cross table enables us to construct a full contingency table with both column proportions and what have you. So I've already installed it, but to install the package, you write install.packages into brackets the name of the command, and then you execute. I've already installed it, so I'll just load it. To load it, use the library command. So I've loaded it, and now we can, if you would like to know more about cross table, you execute question mark then cross table. You write it as it is for help if you would like to know more about it. Yeah, so as you can see, the cross table command is right here, and what implementation of a cross tabulation function with output similar to S plus cross tabs and whatsoever. This is not really important. I'm just trying to show you you can look at the formula. It's very long, but you can customize it according to your needs. So we don't have to put much. We just say cross table into brackets kit A, kit B, then it will give us the cross table, or the, yeah, here's our contingency table, the full one, unlike using the xtabs command. So this is the key. This represents the total counts, and then we have the proportion for the rows, which is this, for instance, divided by 15 gives us this. Sorry, this, the second is a chi-square distribution, gives us this, and then the third one is what we need. That's the column proportion. So it's this 7, for instance, divided by the total is 7. That gives us 1. You see it. 0 divided by 7 gives us 0. That's always the fourth one here. And then 5 divided by 13 gives us 0.35. If you convert this proportion, you multiply by 100, that gives you 38.5, 61.5, 100%. And this is what we've obtained here. Okay. So right now, we can now move ahead and perform our McNemar's chi-square test of independence. To do that, we need a package called Statistics, or Stats. Sorry, I've already installed it, so I'll just say library into bracket stats. If not, you write install.packages into bracket the name of the command stats, because this package actually contains the McNemar.test command used to carry out the McNemar. And then if you would like to know more about the McNemar test of independence command, sorry, you simply write question mark McNemar.test and you execute. If not, you simply go ahead. If you would, let's do it. And here it is. So the command is very simple. You write McNemar.test and then you put what your what do we call it, your data frame or your table, and then you write correct is equal to true. That's for the yet continuity correction. Why is the yet continuity correction important? Because the McNemar's chi-square test of independence, or even Pearson's chi-square test of independence, in the form of McNemar is always 2 by 2 table, but Pearson's chi-square could be 3 by 3, 2 by 3, whatever. But whenever we are dealing with McNemar's chi-square of independence, which is a 2 by 2 continuous table, or a Pearson's chi-square test of independence, which in the form of a 2 by 2 table, the binomial probabilities, that's just these probabilities, these binomial probabilities, what happens is that because these chi-square or Pearson's chi-square or even McNemar's chi-square non-independent, non-parametric tests, there's always they are considered as non-parametric tests because they usually approximate these discrete probabilities to be what continuous probabilities. In other words, to be like they consider the distribution to be continuous, and because of this, let's say our statistic can be biased, so to prevent this kind of bias, especially when it's 2 by 2 table, we have to carry out the Yates correction, because approximation of the binomial probabilities in the form of continuous probabilities makes the test statistic bias. So we have to carry out the Yates correction for the continuity. So you say correct is equal to true, and then let's execute and see. And then you see it has given us our p-value to be 0 point what? First of all, you have to write the table that we've created, which is this. Sorry for the interruption. So this is the table, just the table that we created, our contingency, our t table. Here it is. That's the object that we've written here to perform our McNemar's test. Then correct is equal to true for the yes continuity correction. McNemar, the command is simple, McNemar.test, the brackets table, then correct is equal to true. Let's execute it again. And this is our p-value. Our p-value is 0.0133. So that's okay. We will now go ahead and interpret. So as you can see, this is our p-value, 0.013, right? Okay. And the p-value is actually less than 0.05. So we have to reject the null hypothesis. Why? That's to say the differences that we are observing between 61%, 0.5%, and then 0% is statistically significant in the real population of what? Patients that are tested negative by kit A and positive by kit B, and also in the real population of patients that are tested what? Positive by kit B and negative by kit A. So this difference is statistically significant, and we have to reject the null hypothesis. So we can conclude by saying there is what? A statistically significant difference in test results between patients tested between patients tested positive by kit B but negative by kit A, and then positive by kit A and negative by kit B. And this marks the end of our McNemar Chi-square test of independence. If you have any question, please do not hesitate to leave your question in the form of a comment, and I will reply to you with pleasure. If possible, I'll reply with a video. And please remember to subscribe and be part of the family. See you in the next video. Bye.